Okay, so now it's the second part of today's lecture. Okay, so in the last hour we talk about if we got the kinematic conditions. Right now we have the example problems. We know the U2 is equal to U3, and it is a kind of the kinematic conditions. So in the global stiffness matrix multiplied by the global displacement vector, we will find there are two columns of the stiffness matrix. They are multiplied. Initially, they are different, U2 and U3. But based on the kinematic conditions, we know these two, they are same. So if we add the seventh column to the fourth column, so we have the K14 plus K17 times U2. Also in the second equation, it will be the K24 plus K27 times U2. Okay, since we know the U2 is equal to the U3, so if we add the corresponding two elements together for the fourth column and the seventh column, the results will not be changed since the K14 and the K17 they are multiplied by the same values of the U2 or U3. Okay, so it means that we can reduce the number of the columns. Originally we got 12 columns, but now we can consider only the 11 columns of the stiffness matrix. Okay, then usually we have the same number of we have the same number of the rows and the same number of the columns. If we got 11 columns, usually we need only the 11 rows. And how can we reduce one row from the other? Okay, first remember what you learned in the mechanics of from the mechanics of statics. So if we got a rigid body, okay, so if we got a rigid body, then we can say if there is a force applied inside the rigid body, then we can find some other the so-called the equivalent force system. Okay, inside the rigid body, we can find another set of the force system, and they are called the equivalent force system. And why we call this they are the equivalent force system? Since they can make same or equivalent Okay, since the equivalent force system will make same kinematic response of the structures. First, let me refresh your memory. What kind of the force system they can be called the equivalent force system? First, along the same line, we can change the load point as long as the new load point, they are along the original, if we can change the load point. Okay, if we change along, okay, if we change the load point along the same line, then all these force, they are called the equivalent force system. The kinematic response, it means that we could have the displacement, we could have the velocity or the acceleration of the structures. And for all these equivalent force system, they will make same effects to the structures. And since you can imagine the rigid body, it looks like a very rigid particle. So if we push the particle, the particle will move, it will have the velocity, it will have the accelerations. But if you change the load point, you can say the observe the displacement, velocity or accelerations, they are same. Okay, so it is one kind of the equivalent force system. We can change the load point along the same line. For the rigid body, it will cause the same kinematic response. The other equivalent force system, if we make the force, if we change the load point to some other line, the equivalent force system will be the P plus a bending moment. Okay. If we change the load point to some other points other than the original line, then you can still get a set of the equivalent force. It will be the same magnitude of the applied loadings and along the same direction, plus one bending moment, which is equal to the P times delta. And this one, P plus the bending moment M, it is also a set of the equivalent force system. So you will get the same kinematic response. And but if you check the internal force, the equivalent force system will make different internal force. However, if you observe the movement or velocity or acceleration of the rigid body, they will be same. They will be same. Okay. So that's what we learned from the mechanics of statics. And if we neglect the axial deformation of the beam, okay, original that point A, point B, if we neglect the axial deformation of the beam, so you can say along the axial direction, the beam behaves like a rigid body. So you will have the rigid body Okay, so you can pick out any two separate points, and you will find the relative axial distance for these 2 points. They will never change. No matter the force applied, no matter the magnitude of the force applied to the structures, for any two points along this member, the actual distance will always be same, since we neglect the axial deformation of this element. So along the axial directions, it is a rigid body. Okay, for this element, the A is the point 2, B is point 3. So if we have the force P2x applied, okay, so if we consider the P2x applied, which is the P3x, if we originally have the P3x, which is the horizontal external loads applied to the node point 3. Also, we have the P2x, which is the horizontal load applied to the node point 2. And then we can always say or for the other, okay, you can say all these three, they are the equivalent force system. Of course, it is you can find some other you can find some other equivalent force system. For example, the force can be applied for any inside point, and all these, they are the equivalent force system. Okay, since if you check the response of the structures, the entire structure, not only the response of the element 2, if you check the response of the entire structures, you will find the solved displacement or deformation of the structure will be same. However, if you check the internal force of, especially for the element 2, the internal force will be different. But the equivalent force system will not change the total kinematic response of the structures. Okay, so if you remember the concept about the equivalent force system, then you can say for the original structure, the global stiffness matrix, originally we have P2x, P4x. They are the fourth row in the global stiffness matrix multiplied by the displacement vector. And the fourth row multiplied by the displacement vector can give you the P2x. And the seventh row of the global stiffness matrix multiplied by the U will give you the P3x. Will give you the P3x. so you can get the P2x from the fourth row times the U. You can get the P3x, which is the seventh row multiplied by the U. And also we can get the P2x plus P3x, which will be the, you can add the seventh row to the fourth row. Okay, so you need add the elements in the seventh row to the elements in the seventh in the fourth row. Okay, so if you added the elements, all elements in the seventh row to the elements in the fourth row, then you can get the results and the combined of these two forces. You can say we are calculating the equivalent force system, and right now the equivalent force system which is applied to the nodal point 2. So we can add the P3x to the P2x. However, the combinations of these two applied to the nodal point 2, it is still an equivalent force system for the structures. Okay, so that's the concept. How can we modify the global stiffness matrix? So you will get after you finish the operations, add the seventh column to the fourth column. Also, you need to add the seventh row to the fourth row. So you will get modified K, which is only 11 by 11, which is only an 11 by 11, and the U is 11 by 1, and the P, which is 11 by 1, and this matrix, which is a condensed matrix. Okay, since if you compare the dimension of the modified global K matrix to the original K matrix, the original K matrix is a 12 by 12 matrix, but after you add the seventh column to the fourth column, after you add the seventh row to the fourth row, then you will get a new 11 by 11 matrix. And this matrix, which is a condensed matrix. And for these operations, it is the kinematic condensation. It is the kinematic condensation. Also, we could have some other problems. If you have a structure like this one, okay, for this structure, let's say we have, if we neglect the axial deformation of all beams, okay, so if we neglect the axial deformations of the beam elements only, so in this case you will have the And all of these, they are the kinematic condition. They are the kinematic condition. And how can we modify the global K matrix? Let's take an example of this one. So the node 4, U4, which is the 10th degree of freedom, and the U5 is the 13th. Okay, so the U4 is the 10th degree of freedom. U6, 16th degree. So in this case, the modifications, the kinematic condensation. How can we do that? You need to add 16th column to 10th column, and also the 13th column to the 10th column. Okay, so you will add the original 16th elements to the 13th. You need to add the 13th column to the 10th column. Also, you need to add 16th row to the 10th row. Need to add 13th row to the 10th row. Okay, so then you can condense 2 degrees of freedom out of the structures. So originally, the 15 nodal points, you have 45 by 45. The dimension of the structures will be 45 by 45 Stirling matrix. But if you add the 2 rows and the 2 columns to the same row and to the same column, then you can reduce 2 from the 45. So that's the. Also, you can do the same thing for another floor. You can add the elements corresponding to the U9 and the U8 to the corresponding column and the corresponding row for the U7. Okay, you can do the same thing. Add these 2 to the 10. Add these 2 to the 10. So finally, the dimensions of the structures, you can reduce 2 times 4. So totally will be 8 degrees of freedom can be condensed. So originally the K matrix, which is the 45 by 45. Then you can get a new K, which is 37 by 47. Okay, it is that's the condensed global K matrix. Since we have the kinematic conditions, therefore we can add the corresponding rows and the corresponding columns to the same positions. Okay. That's the simplest type of the kinematic conditions. But sometimes it is not only the beam. For example, if we have a cable structures like this one. Okay, there are 5 joints, and we could have, we need to use 4 elements. Okay, if we got a structure like this one, in these problems, if we neglect the axial deformation, Okay, if we got 4 elements in these structures, also like the same discussions in the last hour, usually you can say the axial deformations in columns, they are more significant than the axial deformations in the beams. So sometimes if you like to neglect some of the axial deformation, sometimes we will choose to neglect the axial deformations for the beams only. Okay, so in these structures, the element 2 and the element 3, they are the inclined beam elements. And also the element 1 and the element 4, they are the elements for the 2 columns. Okay, in this structure, the columns, they are still in vertical direction, but the 2 beams, they are not in the along the horizontal direction. You have some inclined angles between the global X and the global Y direction. Okay, I think let's take a break here, and I will continue it in the next hour.